I will be moderating today's event. For those who are joining first time, I would like to say a few words about this academy and give some technical guidance how to ask questions during the presentation. Rail Baltica is an informal learning opportunity for students across the Baltic states, and we are very pleased to see that students from technical universities from Tallinn, Vilnius and Riga are joining our sessions. In those sessions, we are offering an opportunity to learn from RB Rail senior experts on how to plan, design and construct a high-speed European gauge greenfield rail. Today, we will hear from my colleague Andrejs Mislēvičs, who is our signaling and communications team's leader, and he will talk about how to deliver a signaling system for 870 kilometers long railway line across 3 different countries. We have planned about an hour and a half for this presentation. We encourage you to ask questions during the presentation, because we will stop in between different subjects and answer your questions along the way. So please write your questions in the chat section and we will answer them during the presentation. And from here, I hand over to Andrejs. Andrejs, the floor is yours.
Thank you, Liva. Thank you for this introduction. Hello, everyone. It's a very nice chance to use this opportunity and to introduce the actually the signaling system and the role which it plays in railways. And I would like to share the slides which I prepared for this session. And I believe that somebody from my colleagues would now give me a sign whether it is visible on the screens. Yes, it's visible. Perfect. Let's go to the contents of the presentation. So we have 1.5 hours, and my intention is to start with the principles of railway as a transportation system, to explain how it functions and what are the parts of this system. And this will let us understand why the signaling is needed and how the operations are managed. This would be the second part of the presentation. And as the third part, I would then switch to the ERTMS, European Railway Traffic Management System. This is the interoperable standard for European railways. And thus we will come to the signaling system or signaling solution which we plan for Rail Baltica line. And intention is that at the end of each of these 4 chapters, we will be glad to answer questions, and this could as well take up to 5 minutes. So let's go on with the explanation. What is then railway and how it works? So if we look at railway system, we notice that it consists of 3 following parts. So first of all, traction units or wagons. Then, of course, we need a driveway with all infrastructure required, earthworks, structures, rails, ballast, crossings, energy and catenary system, and of course, station infrastructure for passengers. So this is then the second part. And the third part, which will actually be the subject of this presentation, is control, command, and signaling subsystems, or probably you already heard the abbreviation CCS, which consists of traffic management system, of safety systems, and telecommunication equipment, which is needed to transmit the signals, commands. And on the right side, you see the smooth triangle, which shows that actually that for a smooth interaction of all these three parts of railway system, vehicle, driveway, and CCS, this smooth interaction is needed and is a prerequisite for railway operations. And so, regarding now CCS, why it is needed, we shall understand that railway system have two significant characteristics, which could be explained first of all that there is a driveway or path which is given by the track system, rails. And this driveway could be selected in only two directions on movable elements, switches. Due to this fact, vehicles could avoid each other only at switches, and the driveway shall be set in advance by placing the switches in right positions. So we can call it as a control of direction. As you see here, if the switch is set in deviating direction, then the train will go there. And the second characteristic is that railway has relatively low braking capabilities because of interaction of steel wheel and steel rail. And in combination with relatively high speeds, example of Rail Baltica, 249 kilometers per hour, and high masses, up to 5,000 tons, in case of Rail Baltica, this leads to very long braking distances. So, for instance, if train speed is 40 to 70 kilometers per hour, the braking distance could be longer as the driveway, which is visible to the driver. So, in case of higher speeds, the train driver shall get information on track vacancy by other means. And this function is fulfilled either by trackside optical signals or cab signaling. And this is called, or we can call it, a distance control. And this picture on the right actually shows a fog when you do not see very far a critical situation. And the above-mentioned two significant characteristics of railway system are fundamental for railway operational procedures. And really, due to these characteristics, so first one, need to set up the driveway in advance, and second, need to inform the train driver on vacancy of the driveway. Railway operational procedures shall, first of all, ensure reliable and efficient railway operations in order to provide maximal possible transportation capacity of the infrastructure. And the second requirement is to exclude catastrophic impact of any human or technical error by application of safety measures. And these two above-mentioned requirements on capacity and safety are present in all railway systems, and moreover, often are. meaning more capacity could mean less safety and vice versa. Now I would just to make a short comparison between railway transport and road transport. If you now imagine you are sitting in a car, so car uses infinite number of branching paths limited only by the surface of the road. It's true. If you need to go around some obstacle, you do it. And car driver uses steering wheel to select the best path. Then we have traffic signs, which regulate the driving direction more or less restrictive, but they do it. And direction information is transmitted to the car, but steering itself takes place directly in the car. So, comparing with railway transport, here direction information is transmitted to the driver, the driveway or driveway element, not to the train itself. The element steers the movement of the train by means of wheel-rail system or connection. Yeah, coming back to road transport, keeping the distance when driving occurs on site, considering the absolute braking distance when you are seeing an obstacle, a wall, or end of the road, or relative braking distance if you have a car driving ahead of you. And in this respect, there is probably, there is a rule that the distance to the car which goes in front shall be half of your speed. So in this example, if you go with 100 kilometers per hour, the distance shall be 50 meters, the relative braking distance. And now looking at the railway, as said previously, due to long braking distances, the information about the vacancy of the driveway shall be provided even before you begin the movement. In case if it is not possible, the speed and with it the braking distance shall be greatly reduced in order to enable obstacle detection and timely braking. What is called then that the driver takes responsibility for detecting obstacles and braking. And now let's try to to compare these differences in figures. So on the left side we have a well-maintained car with high deceleration rate and alert driver on a dry road, and on the right side we have dry rails, a railway vehicle on dry rails, and as well high deceleration rate for railway traffic. So actually you see the difference in deceleration, 8 meters per square second comparing with 1.5, and this of course results in the difference in braking distance actually at least 5 times. Theoretically, because I believe some my colleagues from operational department will laugh now and say that this is even not possible to brake a train at such distance. Why? Because mainly if we look now at the high-speed train, ICE2 as an example, with a mass of 364 tons, which breaks down from 250 kilometers per hour, then you just see in the technical description of it that the service braking distance is almost 5 kilometers under LZ-based supervision. So this is the national train protection system in Germany and Austria. And then there is as well a fast braking distance, which could be then interpreted as emergency braking, which is 2 times as short. But still, if we shall consider the braking distance during normal operations, the service braking distance is what is applied practically, because you shall consider optimal utilization of driveway. In other words, you shall not demolish the rails, the ballast. You shall not demolish or use improperly the brake system. You shall think on passenger comfort and safety. And this is then the real example. If you look at the train, which breaks down from 250 kilometers per hour, it needs 4.8 kilometers to break from 250 kilometers per hour to 0. So now short summary on this first chapter. Railways. Railways are track-guided transport systems. It means that the driveway could be changed and other vehicles could be passed only on defined locations, called switches. High speeds and masses, as well as braking characteristics of the steel wheel rail system, cause long braking distances which could not be supervised by the train driver. And based on these system characteristics, it is necessary to control and provide safety to railway operational processes.
Andrejs, thank you very much for the first part of this presentation. I see we don't have questions yet, so maybe our audience is still warming up. There's still more to come. So I think let's proceed to the second half, and I encourage you to ask questions and we will take them off here. I think I got the first question. I got the first question here. Just a second. Unfortunately, it's not displaying properly here on my screen. The question is, how long is the braking distance with wet rails? Is there a difference?
Yes, it is longer. So with wet rails or with ice on rails, of course, it is longer. I would not go now in figures, but yes.
Right. So that was our first question, and I think let's proceed and answer questions during our next break.
Okay. Then we go forward to signaling principles. So let's look now at the functional structure of CCS trackside. Trackside means that this equipment or these functions are fulfilled not on the train, but on the infrastructure side or on the track side. So first of all, describing the picture on the left side of the slide, we have the operation level, the highest level, and the dispatcher is the person who is responsible for several lines or few lines. considering the frequency of the traffic, the level of automatization. And a specific task could be probably even higher than dispatcher, a disponent who copes with delays and rerouting on their entire network level. Then we go one step lower, and then we see that on the operation level, we have a person who is called operator, and he is responsible for directly allowing the train movements. And in the picture provided, you see that this the operator is, or historically, he was responsible for operation in the station area. And then coming back to the equipment level, we see that the interlocking is the equipment, which consists of 3 levels. And on the higher level, operation control level, it provides a man-machine interface to the operator to control the status of the system, of the railway system, of the driveway. The interlocking level itself performs a safety check of operators' commands, and it takes the responsibility for securing the driveway. The third, the lower level is element control level, which performs control and status monitoring of field elements. And these field elements in its turn are located along the track, along the railway track. And we divide these elements into outdoor elements or field elements, and these are switches. These are signals or optical signals which give information to the train driver. These are train location elements which locate the position of the train. And these are as well train protection elements which check the train or which provide the information to the train on permitted speed. This would be the correct description. And if we look at operational task of the operator, then it includes arranging of the train movement from starting point to the target point of the infrastructure, and setting up a driveway for it. So operator is responsible, and the operational process is, if train moves from A to B, then the train shall get a driveway which is dedicated to this specific movement. And looking at the procedure setting up the driveway, it means that physically the switches, which could not be located in the correct required positions, are physically moved or switched into these correct positions. And when the switches are switched, all the following or next procedures until departure of a train and all steps after the train is left point A, and until the driveway could be released for the next train. So when the train came into point B, all these procedures are safety-related tasks to protect switches, to secure the train from rear end, front end, or side collisions with another rail vehicles. So now looking from the operator perspective, this is the topology of the infrastructure which is in responsibility of an operator, and he sees a picture of location of the or usage of the infrastructure. So we noticed that first of all the infrastructure or the driveways which are set are divided into track sections. These track sections, some of them are in red color and they are occupied by a train, and the number, for instance, this number is showing the number of the train, which allows you to indicate unambiguously which train is occupying the section. The track sections is green are reserved by or for a specific train, and as well the number is indicated. Like here you see that the train 1470 is coming on track 6 and is occupying this section, and the next one is reserved for the train which is approaching the red signal. And the white sections are vacant or free. Green arrows represent the signal with permissive aspect, for instance this one, and red arrows signals with restricted aspect. So you see that operator can set up routes for trains, control train movement, and temporarily put track sections out of service when needed for maintenance reasons. So to summarize, any change of the location of the train, or in other words train movement, is allowed only when protected driveway is provided. And in order to meet this condition, the protection of the driveway consists of 7 steps described below. Please look at these steps in the scale of not the complete driveway, which could be 10th or kilometers long, but in the scale of driveway sections, which are actually the smallest possible track sections on which the train movement could be allowed or could occur. So looking at these steps, you have first one, you have checking the, so this is then the function of the trackside CCS. Checking the driveway means, first of all, is the driveway free? Are all track sections free? Are all movable elements in right positions? If no, then the route couldn't be, or the driveway couldn't be set for a specific train. If yes, then you can set up, then the system sets up the driveway. All switches in right positions, yes. If it could be done, then it shall be checked whether the driveway is locked and the protection to the driveway is provided. Yes, the driveway is locked, so switches could not move. And the train movement could be allowed. And this is the command which could be transmitted to the train. Yeah. For instance, with the signal aspect, you can go. Then the next step is actually the checking on the train or vehicle whether vehicle could depart, what is of course as well important. When it is the confirmed, then the system protects or maintains protection of the driveway until the train uses it, and only when the train goes out of this driveway it could be released, or elements of this driveway could be released. So the idea is that the train movement is allowed only when all assumed hazard possibilities are effectively excluded, and for the time of the movement of the train remain excluded as well. Now we switch to train side functionality and functional structure of train side. As said previously, the train driver receives a driving order, and classical way to transmit a driving order is by means of the optical signals. Optical signal which is visible to the train driver. According to this driving order and to the timetable, the train driver operates and controls the train. So the train driver is responsible for starting the movement and operating. Number 3, this is the subsystem or functionality called train protection, which enforces driver to note safety-related driving orders. So the train protection influences train control independently from train driver. For example, when the train is passing the red aspect of the signal, the train is break down. And number 4, this is the train location system, which is using data acquisition methods for train location to locate the train. So the train driver follows driving orders. His actions are supervised by the train protection that triggers the emergency braking in case of human error. Now let's look in more detail at the functionality of the train protection system. As explained previously, the driving order is primarily given by an optical signal, and this optical signal provides information or multiple information. So first of all, it provides information on availability of the protected driveway, or in other words, whether this driveway is available for the train. Then the optical signal provides information on the allowed driving speed. and the optical signal as well could provide information on the aspect of the next signal. So, in other words, on the length of the driveway, on the length of the protected driveway. And the train protection in its turn monitors how train driver is following the driving orders of the optical signaling. For instance, train protection performs braking before the hazards. For instance, signal with the restrictive or red aspect. And the train protection itself could be implemented as punctual train protection, what is mandatory for speeds from 100 to 160 kilometers per hour. And as well, the second implementation possibility is continuous train protection, where when drivers shall follow the permitted speed continuously during the entire trip. And this system is mandatory for track speeds higher than 160 kilometers per hour. So the important message at this point is that the train protection system consists of both trackside equipment and train side equipment. So for train protection, you need system on board of the train, and you need system located or equipment located along the track. Yes, now let's look at the braking curve. To explain in more detail the function of punctual train protection and continuous. So punctual train protection means that the train speed is checked or supervised only at specific driveway points. So for instance, on the diagram on the left side, these are points 1, signal with yellow aspect, and point 2, signal with red aspect. And the idea is that the speed check at the location of the signal with yellow aspect shall supervise that the driver goes with the reduced speed and is ready to brake at the signal with the red aspect, where the speed shall be under a specific limit. And continuous train protection checks the entire yellow braking curve permanently. Such type of a train protection is mandatory for track speed higher than 160 kilometers per hour. And it is obvious that continuous train protection requires more complex and more costly train and track side equipment. What would be interesting or necessary to remember or to understand that this punctual and continuous train protection systems are two different systems, and most railway lines are equipped with both systems just because of mixed traffic, that you have slow trains like freight trains, and you have high-speed trains, international trains, or for redundancy reasons, when you say that in case if the continuous train protection is malfunctioning, then you have a redundant system which provides you a fallback solution with reduced speed. Good. And I believe these were the main things I would like to explain you about the signaling principles, just to remind once again the main ideas. So the driveway is set up before the train movement is allowed, and the driveway is maintained until the train leaves it. Train drivers' actions are supervised by the train protection that triggers the emergency braking in case of human error. And in relation to Rail Baltica, train protection with continuous supervision of the train speed is required by the speed higher than 160 kilometers per hour.
Thank you, Andrejs. We have a couple of questions in the chat. I will start by this one from Tom Zalans, who is asking, how will you ensure safety of both freight and high-speed trains using the same railway line?
Yeah, but I mean, with the same system. I believe I do not see the difference between ensuring safety. I believe that here we are speaking about train protection for freight trains and for passenger trains. So in this case, it will be a single train protection system for both types of trains, which will provide the safety level required and as well the interoperability required for the cross-border operations.
Good. And then we have another question about what will be the braking distance for trains in Riga between the two stations. So how will the trains reach up to 250 kilometers in that section?
Yeah. Yeah. I would like to, as well, to go step back and to explain the idea of the speed, or how the speed could be reached by the high-speed trains. As well, if we go back to our system overview, we have train, we have driveway, we have CCS. For instance, we have a train, international train, high-speed train, which could go with 250 kilometers per hour. Good. It's like a Ferrari in Riga. Then we have a driveway. And the driveway is designed according to special constraints, according to some space limitations. For instance, in Riga, the approach is to go with Rail Baltica along alignment of 1520 network, LBZ network. It means that this alignment sets a limitation on the speed of Rail Baltica alignment, namely meaning that the speed which it could grant you is not 250. It is, I would say, in the range of 120 kilometers per hour due to the special constraints and curves, which are the limiting factor for the speed. So then you see, like, you have a car which could go to 150, but the permitted speed on the line is only 120. It means that you could not go higher than permitted speed, 120. And then on top of it, you have CCS or signaling looks at the utilization of the infrastructure and the distance to the train which goes before you, ahead of you, and which could even look at the quality of the track and say in normal conditions you could use this track with 120, but due to some construction works you could go only 60, and then the signaling limits your speed to 60, like saying we have some maintenance works or and looking at the system, so you have the speed provided by the driveway, you have the speed of the vehicle, and you have a speed which is then controlled by control command and signaling. And the most permissive speed shall be then transmitted to the train driver. And answering then to the question, for instance, in Riga, it is not possible from the driveway point of view to go at the speed of 250 kilometers per hour.
Thank you, Andrejs, for your question. Let's take one more question. This is a question about whether Rail Baltica is planning to implement electromagnetic brakes for rolling stock.
Good question. I understand that this will then be a requirement to the quality or strength of the track. I would take this question with me, and we can answer it later, as I could not do it now, unfortunately. So if you could note the contact information of the person who raised this issue.
We're taking note on Fyodor's question. And there's one more question regarding traffic management system and whether we're considering the use of 5G. But Andrejs, you will talk on this question in the next part.
Yes, 5G we will touch regarding traffic management. If you see any details of the question.
What traffic management system is planned to be used on Rail Baltica?
I do not understand, frankly. What answer you expect?
Okay.
What kind of a standard? This we could explain in the last part when we will describe our solution.
Yes.
Probably, if this question will not be answered in this chapter, please ask again, or probably reword the question.
Okay, so this is for Andrejs Mislēvičs. So if we don't answer your question going forward, then can you just maybe give a bit more detail on your question in the chat? But I think let's then proceed, Andrejs, with the presentation.
Thanks. Yes, and then in the previous chapter, talking on signaling, at the end I made more, I emphasized the need of train protection system. And in this chapter we will look at particular train protection system called ERTMS, which is the standard for European cross-border traffic. And they talking about the lack of unified standards in railway. Let's look once again at other competitive transportation segments, like in automotive. For cars, you have standards for a variety of systems and vehicles, and we have compatible traffic signs, so we have compatible driving license, and it is not a problem to go across the Europe from any Baltic state. In airline industry, it is even, I believe, better, because it is really worldwide standards which allow to have unified traffic control, aircraft control, international approvals and international pilot licenses. And we look at railways, and the situation is that there is the diversity of different suppliers, diversity of different systems, including and interlocking, diversity of communication systems, and even rolling stock. The trains are incompatible, or national standards are incompatible. And the main problem is that the unified system for railways was historically missing. And then going closer to CCS, or train protection in this case, if we look at Europe, we have 32 countries, 32 railways, over 200,000 kilometers of railway, and approximately 100 different communication systems, and more than 13 different national signaling or train protection systems. And there are, as mentioned previously, systems for speeds up to 160 and for speeds above 160. And the problem is that the railways were developed at the times when national interests prevailed, and railways were considered as strategic infrastructure which shall be kept on a national level. And then the ERTMS system, from European point of view, is the vehicle which shall overcome these historically grown technology barriers of the international railway sector. And the idea behind ERTMS is that it will gradually replace existing incompatible and supplier-driven control and command systems in the Europe, and probably as well in worldwide. And the benefits are that the standardization and interoperability will help railways to boost, to operate international freight, international passenger, and decrease system cost. So what railways receive is the universal system. It provides increased track capacity and safety. It provides increased reliability, reduced journey time, cost decrease, and strengthening of internal European market, and as well export market for European railway industry. And then if we explain, or if we look at subsystems of ERTMS, we notice that the basis or communication platform for ERTMS is a mobile system called GSM-R. So it is GSM, which is further developed for railway needs. And this platform provides a bearer or communication between train or railway vehicles and infrastructure, and is used for several applications. So first application is just the voice communication between train driver and the operator or dispatcher. And the second application, which provides train protection, is called ETCS, or European Train Control System. And there is as well the third application, ETML, European Train Management Layer. In my praxis, I did not touch it, or I was not deeply involved in this one. And of course, it is a possibility to develop further applications. And I believe that with 5G technology, it will even be of more interest to have these further applications. And so ERTMS provides voice mobile communications via GSMR and train protection, ETCS, which are crucial for interoperability. So please understand interoperability as the possibility for a specific train to go into cross-border operation in different countries, so to cross borders between countries and use the same onboard system. So what is now ETCS if we continue to talk about train protection? ETCS ensures adequate safety margin between trains. Yeah, here I have a statement that it increases line capacity, question mark, keeping in mind that capacity and safety are often two sides of the coin. It's, I mean, there are many projects where it was aimed at the very beginning, but as ETCS increases the safety, it reduces capacity automatically, especially on existing systems. So, and how does it happen? Speed limits are transmitted from track to the train. Driver's screen shows permitted maximum speed, and onboard computers stop the train if the speed limit is exceeded. So main idea, what is behind ETCS, or the function which is fulfilled by ETCS, that it brings trackside signaling or optical trackside signals into the driver cabin. It allows reduction of complexity for train drivers, so more automation. It provides information on the onboard display, and it allows, it also controls the train speed permanently. And on the right side, you see a picture. So this is the MMI interface of the MMI of the train driver, and I don't know whether it is visible, but this is the permitted speed, 160 kilometers per hour. The arrow shows currently the current speed of the train, 153 kilometers per hour, and on the left side we see the length of the protected driveway, which is 2,180 or 90 meters. And this sign shows the permitted speed at the end of the driveway. So in other words, the train shall brake in 2.1 kilometers from 160 to 0. And of course, this limit is adjusted dynamically. So with each meter towards the end of the protected driveway, the allowed speed limit is reduced. And ETCS reduces complexity of signaling and optical information, which shall be then in conventional system be obeyed or controlled by the train driver, and decreases the risk of human error. Yes, on this slide, probably the next step or the next level of detailization, which could explain you the different implementation possibilities of the system, is distinguishing between ETCS level 1 system and level 2 system. And level 1 system is practically a system or train protection system which is suitable or could be applied for speeds up to 160 kilometers per hour. And information on the length of the available drive wire in ETCS level 1 is transferred from the optical signal to the train onboard computer by means of Euro balise, which is located in the track. And an onboard computer located in the train calculates the train braking curve based on the permitted speed, train location, and distance to the danger point. So ETCS level 1 ensures continuous train protection. It means that during all time of movement, the train has the continuous braking curve or speed limitation or speed maximum speed, which is supervised. And the data transmission itself is only on specific points where Euro balises are located. And the second implementation level of the ETCS is the usage of GSMR or radio system for transmission of the data between infrastructure and the train. And in this system, it is used for transmission of the information on length of the available driveway. And onboard computer then calculates the braking curve and the same parameters on board of the train. And this system has both continuous train protection and continuous data transmission and is applied for speeds above 160 kilometers per hour. To summarize, so ERTMS is EU standard which is needed for development of EU-wide interoperable railway services. I can even say that it already became an international railway standard for high-speed lines. ERTMS brings the optical trackside signals into the train driver cabin, thus making it obsolete or not needed. And the third point, which I would like to mention as well, that complete migration to ERTMS in Europe has faced significant delays. First of all, due to long and costly migration from national train protection systems, from all this variety of different systems to the single or to the one solution. So it's not so easy to migrate, keeping the railway in operation.
Thank you, Andrejs. We don't have many questions yet, but we have one. So we have a question regarding GSMR services. So the support of GSMR services is doubtful after 2030. What is your plan B solution? Satellite or FRNCS system?
Mm-hmm. If you allow me to answer this question in the last chapter, where we will look at solution or CCS solution recommended for RB Rail, and we will as well touch this question in particularly. So the obsolescence of GSMR as a old technology, and what options do we consider? What options do we have?
Okay, very well. So we will answer that question.
We will, yeah. I would propose we will answer it later, and then, yeah, if.
Mm-hmm. Okay, another question just came in. Along ERTMS, will Rail Baltica install, and here traditional signals or just block markers? Block makers.
Yes, very good question. Last chapter, the same. It will be answered then in the last chapter.
So I'm very pleased that our viewers are already predicting what is your next. That's it from now. I think let's proceed to that chapter that obviously everyone's interested in. So
very good.
Let's go ahead.
All right, let's go ahead. And then after this, I would say introductory part. I'm pleased to see that questions are becoming more and more precise. And let's look at the solution proposed for Rail Baltica, but from the very beginning, let's look at this slide. I believe that some of you already seen it, which I would call as Rail Baltica fact sheet, describing that, for instance, it will be 870 kilometers of greenfield railway infrastructure, double track, ERTMS level 2, electrified 2 times 25 kV AC. The maximum train length supported by station or loop tracks will be 1050 meters, axle load 25 tons, and design speed for passenger trains to 49, and for freight trains 120 kilometers per hour. And the loading gauge will be a Swedish one. And if you look at the map on the left side of the slide, you will notice that the green color shows the international stations, 2 in Estonia, 2 in Latvia, 3 in Lithuania, and the yellow color depicts the freight terminals on the entire route from Tallinn to Kaunas, Poland border. And now, if I may very briefly explain the main characteristics of the CCS subsystems or CCS solution, which is recommended for deployment by the CCS Deployment and Strategy study, then it recommends that we, as a project, base the solution on the next release of CCS TSI specifications. So this is the technical specification for interoperability, in this case for control, command and signaling, which is the standard describing the subsystems mandatory for any high-speed lines in Europe and corridor European railway TNT corridors. And the current one issued in, if I remember correctly, in 19, still defines the ETCS and GSM-R as the standards. And it is expected, and we wait for it, that in 2022 the specification will standardize the next generation of radio communication solution, namely now it is called FRMCS. And yeah, what of course will allow us to avoid purchasing and implementing a technology which is completely obsolete and based on 2G standard, which is already a history. And then so for train protection, it remains ETCS level 2, and there are as well two standards which will be, or specification standards, which are proposed to be a basis for interlocking system and for traffic management system. I would not describe probably it in more detail now. What I would like to mention that the idea or the target for Rail Baltica is to have a single design concept for entire line, so for 3 Baltic states, which will allow to use this scale of economies, and moreover, which will allow to minimize the number of interfaces between countries. And as ETCS solution, it is targeted to have a level 2 without trackside signaling. Location will be provided by Excel counters. So, as already said, radio communication FRMCS standard based on 5G. Automatic train operation functionality, and from practical solutions, we look at the concentration of equipment in so-called block system locations or specific sites which will accommodate all equipment needed. One of the targets is to completely avoid copper cables on open lines, which will allow to minimize the investments needed, and as well to use renewable electricity supply on the block system locations with the low power consumption. So mostly Excel for where we have only Excel. Yeah, coming to one of the questions, I believe that it is better to show a few pictures explaining the type of equipment or type of solutions which will be or are planned to be installed for such configuration of CCS. And on this picture, we see in particularly the marker board, which is the static table, and which fulfills the role of the signal in the ETCS equipped on the ETCS equipped tracks. And this equipment is an Excel counter which defines the border of the track or driveway section and used for train location. And this two balises are part of ETCS level 2 and are fulfilling a function of calibration of the odometry for location of the train. Yeah, here's another one picture showing that the ETCS marker boards are, well, could be located at catenary poles in order to use or reuse these poles for signaling system. And the same, you see the balises here in the track. Another picture, the resolution is not optimal, but I believe that this is very typical track layout of one side of the station or loop for Rail Baltica, where you have mainline tracks with design speed going through the station and two sidings which provide possibility to overtake freight trains or to stop some regional trains. And the station is as well equipped with you see marker boards so ETCS without trackside signals. And now coming to FRMCS, I put as well few pictures showing the masts or towers located along the track, and in particular the antennas are still from GSMR, but the FRMCS as the new solution will be then slightly different. And talking about automatic train operation functionality, ATO, which as it is planned will be as well standardized under TES ICCS specifications. The idea is, if you now look at the MMI picture shown previously, that the allowed speed or braking curve is of course calculated from the safety point of view. So it answers the question, what is the permissive speed in the current moment for the train in order to brake before the danger point. And the automatic train operation gives, I would say, it is more sophisticated, and it is complementary to ETCS, showing not the permitted speed, because it could be higher as you need to go, because the traffic management system will know that in 20 kilometers you have to stop and to wait. And in order to avoid this breaking down from 160 to 0, and then accelerating again, and what costs time and what costs as well the energy. It could be more smart to go with 100 kilometers per hour from beginning of this section, and then you will not need to brake. And this is the main idea behind the ATO. So if we now are very honest and talk about our challenges. First of all, we still believe at RB Rail that the main challenge is to have a single design concept for CCS subsystems and single operational rules across 3 Baltic states. Why? Because in case of differences, the implementation of this ETCS national specific functionality will definitely increase complexity of a solution, meaning time and cost. And we know as well from other project experiences that this could result in a situation that the interface between ETCS in one country and ETCS in another country will result in a different the different project, which will be not easy to manage. So the second challenge is that there is no ETCS experience in Baltics. So no ETCS line in operation in Baltics, and GSMR network is in operation only in Lithuania, GSMR for voice. Then, of course, the problematic of short life cycles of mobile communication systems, for instance, GSMR S2G technology, and that already led to situation in Europe when the new standard, which will be based on 5G, is not yet standardized, and the railways still shall maintain the old systems. So the question was very correct, and when we ask ourselves as well, shall we introduce 2G in case of delays in standardization of 5G? And the current answer is probably not. Then as well, based on European experience, if we look more deep in railway operations and in ETCS solutions in other countries, optical signals are not completely avoided and are used for local operations. I mean shunting operations, like local operations in yards, where it is very costly to introduce ETCS, and in European countries it's not a solution. And the question for us is, shall Rail Baltica follow this approach? Shall we keep optical signals for local operations, shunting operations? If yes, then which national solutions, different in each country, shall be followed? And the next challenge is, in my mind, very significant, and it is relevant for cases when there are one-level crossings with existing 1520 infrastructure. In each case, it requires the development of a dedicated solution which is not available on the market, and it requires the interfacing of ETCS with some already existing or probably old interlocking systems, and this could cause as well a lot of effort. And I think it was the last one. Challenge.
Certainly, we have enough of challenges, but there are 2 very practical questions. So driverless cars, is this reality on Rail Baltica line? Driverless trains?
I would say I would say it depends on. It depends as well on operators, probably, because one thing is the of course operators and infrastructure, but for instance, if we look at completely driverless, so first of all, it's not so indeed. So the question could be, I would say, current design approach, no, as in order to have completely driverless trains, you need to control the gauge. So you need to control the complete area of the railway for the case when you can have an obstacle there, like an animal or people or something is falling down. And I mean, currently it is not the requirement of Rail Baltica. I know that you have different solutions to control it, so you can control it as well from the rolling stock, from train. But then it is the really I would say the different assignment for an operator and for infrastructure manager to agree on principles and agree on the system, how this completely driverless train operation is allowed. So what I was explaining in this ATO slide was rather a driver advisory system, which means ATO level 1.5. And the question was now, if I understood correctly, related to ATO level 4, when you have just nobody who could operate the train on board, and all operation is performed remotely. So I believe that ATO 1.5 to level 2, this is reality. Yeah, for Rail Baltica is yeah.
Lovely. We have 3 more minutes, and I think I'll take this question, which requires a clarification about the different speeds that you mentioned. You mentioned operational speed, which is 249. We also speak about the design speed, but we also mentioned 250 for high-speed rail. So can you explain the differences between the design and operational speed? And why we sometimes mention 250, like in this presentation?
Good question. I mean, you have design speed, and this is the requirement which you give to your designer when it designs infrastructure, so track itself, and then this track design has as well a margin of safety. So, for instance, in Germany, if they put a new line in operation, they perform dynamic tests with train speeds plus 10% to the future operational speed. It means the margin which is provided. Then the clearly operational speed is the speed on which infrastructure manager. So when the line is constructed, it will be an entity responsible for management of this infrastructure. And operational speed is the speed at which infrastructure manager allows you to use this line. In my understanding, why we have 249, if you look at standards in TSI, you will see that the standard of a specific category of line prescribes that the speed is up to 249. And the next type or standard of the line is 250 and higher. And from practical reasons, it means that you will need all systems for the line which will provide the speed up to this limit. So in order to be conform to SI requirements. This is why here we have a figure of 249.
Very well. Thank you, Andrejs. And I think by this we will conclude the questions. This is indeed our time to end this presentation. We've been very punctual, and as railway should be, right? So I just thank you all for your attention and participation in large numbers. We're waiting for you back, same time, same place, next Thursday at the same time, when we will have a presentation from our colleague Jean-Marc Bedmar, who will speak about Rail Baltica electrification plans. So come back for us. This is also an exciting topic, and maybe think of your questions in advance. We will be certainly happy to answer them. So by this we conclude, and thank you very much, and thank you, Andrejs, and we meet again next week.
Thank you. Bye-bye.